So an arithmetic sequence was one in which we added a constant value to a term to get the subsequent term. In a geometric sequence, what we're doing is multiplying a common number going from term to term. So in this example, we are multiplying by 3 each time we go from one term to another. So if we take the second term divided by the first, or the third term divided by the second, or the nth term divided by the term before it, n minus 1, we get a common value. In this case, 3, and that number we call the common ratio, indicated by variable r. Now, of course, the question we're going to want to know is, if we kept this sequence going, let's say on and on and on, and we wanted to know the 10th term or the 100th term, is there a way we could get that without having to actually write out all the terms? So we're going to do similar to what we did with the arithmetic sequence, and we're going to look for a pattern. The first term was 2. The second term, we get that by going 2 multiplied by 3. We have one jump of the multiplier r. The third term is the starting term times 2 jumps of the multiplier r, another multiplication of 3, which we could write as 3 squared. And to get to the fourth term, we're going to do our starting point and 3 jumps of the multiplier r. And so you'll notice that in general, to get the nth term, it's always our starting value, in this case 2, and then our multiplier, in this case 3, we multiply n minus 1 times compared with the term we're looking for. So for term 4 it was 3 jumps, for term 3 it was 2 jumps, for term n it's going to be n minus 1 jumps. And this is the general term of this particular geometric sequence. So if I wanted to know the 100th term, I could plug 100 into that formula and out it would come. So just to generalize this process, term 1 is term 1, term 2 is term 1 times r, term 3 is term 1 times 2 multiplications of r, term 4 is term 1 times 3 multiplications of r times r times r, and so Tn is the first term times n minus 1 multiplications of r. And this is the formula for a geometric sequence. Alright, so we have our formula for a geometric sequence, and as with an arithmetic sequence, if I know any 3 of the 4 variables, I can algebraically solve for the fourth. So I have a situation here in which I have a geometric sequence. I know that term 1 is 10, and I know term 5. So let me just map out the other terms. Term 5 is sitting here at 6250. And the question is to calculate the other terms. Now, possibly you could do this by trial and error if the numbers happen to turn out nicely. But really the key thing we're missing is, what do we have to multiply by? What constant number do we have to multiply by in order to land at 6250 on the 5th term? And so instead of doing this through guess and check, I'm going to apply the formula. So what do I know? Tn, in this case I know T5. Alright, so n is 5 and T5 is 6250. So I'm going to substitute that information into the formula. 6250 equals term 1, which is 10. The multiplier r is what I don't know, so that stays as r. And in this case my n was 5, so 5 minus 1 is 4. And if I solve this equation, I can come up with the value of r. So I can start off here by dividing by 10. So I could do the 4th root of both sides. Now I need to be careful here because when I do a 4th root, there are 2 values, plus and minus. And you can go to your calculator. I just happen to know that that's 5. Alright, so I've got plus and minus 5. Now you might be wondering just a little bit about the plus and minus, so let me just explain in detail what's going on with that. So what I'm basically saying here is, if r was 5, I would have 10. I would multiply by 5 to get 50. I would multiply by 5 to get 250. I would multiply by 5 to get 1250, and then multiply by 5 to land there. Okay? But we would also use negative 5. And you're saying, really? Well, if I multiply by negative 5, I'm going to get negative 50. Multiply by negative 5, 250. Multiply by negative 5, negative 1250. And sure enough, multiply by negative 5 lands me at 6250. So in this case, I have two possible sequences that work.